Hello, I'm Elias. I'm part of LNG, and this is a presentation we did. The initial idea was actually we thought of the initial plan on the previous Connect with Francois and Mikita, who is unfortunately not here today, did help on developing the whole idea and the proof of concept. So we essentially tried to move the data path of the kernel from the kernel space to the user space for a number of reasons. So one of the reasons we try to do that is that time-sensitive networking seems to be an increasing interest in the industry. So it initially started as an idea for industrial IoT devices, automotive, and audio-video applications that require really low latency. We did do a measurement on the Linux kernel, and we figured out that the latency in most of the cases is enough. But the problem with the TSN approach of the Linux kernel is that it requires a really specific amount of jitter it can tolerate. And the Linux kernel, on most of the cases, isn't capable of following that. So moving the obvious solution and the easy solution is to move everything on the user space so you can eliminate the jitter. So apart from the latency that the Linux kernel usually follows up, you have applications that require extremely low latency, which you can't follow up from the kernel as well. So you need applications with a microsecond of latency, and you can get that if you configure 5 switches as cut-through on the whole path. You can actually get 1 microsecond latency. As we said, as you can see, the Linux kernel latency, this is the adapter application latency. It's 20 to 40 times that, and it's 260 times up the jitter. That's on average. So one of the cases was that. This is also good because it was developed. There's an Open Avenue alliance that's actually there to make an interoperable ecosystem for the TSN, and right now they have an implementation based on the Intel i210 adapter, which does exactly the same. It maps specific queues of the hardware to the user space so they can use it for the TSN applications while they let the adapter deal with the rest of the traffic on the kernel space. So that's what OpenAvenue currently does, but it's only supported on one network interface, and they've actually forked the kernel driver for the Intel i210 interface. Another thing is that the kernel can't do line rate at the moment on 40 gigabit or above, and actually I don't think it can do even in 25. Line rate is what you get on 64-byte packets. So on 40 gigabit, you're talking about roughly 60 million packets per second, which is a pretty big number. It's actually close to 57. The Linux kernel already has an approach on that, but it's called VFIO PCI, and it was mostly used for virtual function devices, so you could unmap the device from the kernel and you could remap it to the user space and then have a VM take over it. So you had the VM using the device, the kernel didn't do anything about it, but you had the driver on your guest operating system that was able to use that, and you could take advantage of the device. The DPDK project that does something similar. So it unmaps the device from the Linux kernel, but then you have to rewrite the whole driver on the user space. And you have to handle the device from the user space. You have to reset it, take care of the interrupts, make sure that the device is okay, keep in mind that there are different hardware erratas and complications on the resets, and you have to do that all from the user space to get the traffic over there. So here's what we try to do. There's a mediated device framework that's already been upstreamed on the Linux kernel, and it's been part of the kernel since .410. It was initially implemented and introduced by NVIDIA, if I remember correctly. And it's actually based on the same idea, providing mediated devices for the GPUs. Intel actually has an upstream kernel. On the kernel, there's a GPU driver from Intel that's already upstream, working, and it's based on the same idea. Now, the advantage of that is that the VFIO framework in general uses the IMMU whenever it's available in order to configure the devices, configure your memory spaces, so you can restrict devices on respective domains, and you can minimize whatever risk you have. Now, the approach that we tried and what we try to do is that it greatly simplifies the driver that you have to write on the user space. As we said, in order to get a device to the user space with VFIO, you need to rewrite everything. So on average, if you have a look on 10 or 40 gigabit or 100 gigabit interfaces, you're essentially talking about 30 to 60,000 lines of code. And apart from that, you need to follow the upstream. So whenever there's a kernel change on anything, you need to do the same on your driver. So you need to follow the upstream and constantly fix your driver over and over again, or fix it if there's a new errata on the hardware, or fix it if there's a new hardware revision. So you have to do the whole thing, scan the bus, figure out the devices there, and reconfigure it from the beginning. Now, what we tried to do, we ended up with 1,000 lines of code for a full driver. The 1,500 is there just because we haven't covered all the functionality of the devices. So, for example, we don't have VLAN support if the device has it, or segmentation of loading. But overall, we don't expect to get more than 1,500 lines of code to get a full functionality on the user space. As we said, the advantage is that you don't have to deal with anything. You don't care about interrupts. You don't care about hardware revisions. How weird is the hardware on resets? The only thing you care about is how you're going to get the descriptors on the user space and how you're going to get the traffic on the user space. In order to do that, you'll also require some lines of code in the Linux kernel as well, which is usually less than 500 lines. So the advantage of all this is that this is not just Ethernet. As we said, Intel is already doing this for i9-15, and there's an approach from Huawei who's trying to do a similar thing for crypto devices. So this is not only limited to Ethernet. This has a broad approach to pretty much every device that works the same way. Another thing is that we can support zero copy, and zero copy seems to be paramount when you're talking about 100 and 200 gigabit networks. The memory pressure is actually going to be pretty high on the system, and you need to be able to have applications working as well, apart from your network traffic only. So what we're trying to do eventually is get the best of both worlds. You get your existing user space tools to operate. So you get Ethtool to operate. You can configure the device. You can configure the number of rings, the number of descriptors. You can read the registers, whatever you can do with Ethtool. Ifconfig and IPRoot are still going to work, and TCP dump is going to require a minimal amount of effort to be ported, since it's just a matter of where you read your buffers from. Another thing is that we've done this for 5 Ethernet interfaces at the moment, and the thing is that there's a different approach for hardware vendors for every hardware interface out there. So what we refer as slot mode is that when you receive a packet, you allocate a number of arrays that's usually 248 bytes to receive packets. So imagine that you only want to receive 64-byte packets. So actually, you're going to dump the whole array, and you're going to waste a bunch of memory just to receive a packet. This is what we call slot mode. So it's a structured array, and you place each packet on one slot of the array, and you move on and on and on until you have to recycle it. Now, there's specific ARM SoCs that have multiple arrays. So you have 120-byte arrays, you have 256, 512, and the interface decides where to place the packets. So you actually minimize the memory loss from that. Now there's a last category of NICs that we call tape mode. What they do is that you don't actually feed the hardware with an array. You feed it with unstructured memory, and then the hardware just decides where to place the packet, and you get the descriptor describing where the packet starts, where the packet stops, how long it is, and how you can pick it up. So what we're trying to do is that we're trying to support all 3 modes of that from the user space. Now the last thing is that we're trying to keep it bus agnostic. At the moment, we've only worked with PCI Express devices. But the whole design, the idea on the module is that we will be able to support any bus that hosts the device. So we don't really care if it's a PCI or if it's DPAA on ARM or anything like that. We only care that for specific hardware areas. Now there are some goals and limitations. As we said, we need to be able to use any I/O model. So apart from the NICs, there's DPDK, ODP, or VPP, and every one of those projects have a different memory model. So we need to be able to adapt and support all of them. For now, we've done this work for ODP, so there are drivers for ODP which you can use and try today. Now, there's also an AFXDP project posted on the Linux kernel mailing list at the moment, which is rather interesting. But the problem at the moment is that it's only limited to one model of NICs, of network interfaces. So it only supports Intel cards mostly, which use the slot mode, the array mode that we discussed. Another goal of the project is that we need to be able to do line rate, even on 100 gigabits. Now, 100 gigabits interfaces is probably going to be limited by the PCI transaction limit on that. So that's not really doable at the moment, but with future buses PCI 4, we might be able to do that. Another advantage of the network interface cards that use tape mode is that you can somehow trick the PCI Express transaction limit and squeeze in more packets than you can on slot mode. So if you're talking about high-speed NICs or high-speed applications, you really need to move to that memory model in order to have really good performance at the moment. Another goal is that we need to expand to anything more than network interfaces cards. As we said, Huawei is doing a very similar thing on crypto devices, and we should be able to collaborate on that because it's pretty interesting. And Intel i9-15 is already there on that. So ideally, we would like to provide a user space API for the user to try and do user space drivers as minimally as he can, with the less effort that he can, and the amount of bookkeeping that he has to do or upgrades that he has to do, depending on what's happening on the kernel, is going to be way less. It's going to be way less limited than what he has to do right now with DPDK. Now, one limitation is that we try to figure out if we need to do it on cache-coherent hardware or if we don't, and we try to find non-cache-coherent hardware to do the same tests. As you can imagine, if you're talking about 100 gigabit interfaces with 148 million packets per second, 148 million system calls, it's actually not going to do the performance work. We did find some interfaces that you can cache flash or invalidate from the user space, so you don't need a system call, but unfortunately all of these were cache-coherent. So we ended up on the fact that we're probably not going to run on non-cache-coherent hardware. Now, let's see, this is a code overview of what we had to do and what was on the Linux kernel. So what you see on the original means what's the Linux kernel driver or the DPDK equivalent of that. Kernel means the line of changes, the line of code we had to change on the kernel driver to make this operational. And user space is the amount of the user space driver we ended up writing in the end. So as you can see, Celsius started from 48,000 lines of code in the Linux kernel. We had to write 500 lines on the kernel because this was probably the most complicated interface we had to deal with. And the user space driver is close to 1,000 lines. Intel was more lines on the kernel, but it ended up needing less additions on the kernel and even less code on the user space because slot mode is way easier to handle on code. The E1000D was the interface we used as proof of concept because it was really cheap and it supported anything we wanted. So as you can see, we started with 30,000 lines from the kernel. And since this is a 1 gigabit interface, it was even simpler for us to do the kernel implementation and the user space configuration and handling of the descriptors. We also did a Realtek interface as a proof of concept, but this is discontinued. It was also a 1 gigabit interface, but the number of lines of code were similar, so that's what we were looking at in the end. Right, this is some raw performance that we have, and we focused on TX first because TX was easier to get working. RX is not optimized yet, and it's not optimized because we're pretty much getting the same number with 1 and 8 number of cores, so we're trying to figure out what we're doing wrong. Most of the results were achieved using 4 CPUs. For the Intel card, we just used 3 CPUs, 3 cores. And Celsio T4 and Intel, the 40 gigabit Intel implementation was tested on a Core i5, and the Celsio T5 was on a Xeon. So here's the numbers. These numbers, we got these numbers with ODP using the native ODP generator application, which is able to transmit its raw receive and transmit packets. So on the 10 gigabit interface, we get 8 million packets per second on the receive side. We get 13 on the TX side, while the line rate on 64 byte packets is pretty much close to 15 million packets per second. Now on the T5, which is a 40 gigabit interface, we get 10.3 on RX, but that's on a single core. And we got 48 million on the TX, and the line rate is 59.52 million packets per second. The 48, I think we can't get more than that on Celsio, and the reason is that DPDK is giving a performance implementation on that, and it's on Celsio website. So Celsio is saying that the best performance they got up to now using DPDK is this number exactly. So I think we reached hardware limits on that, when we can't go above that. This is interesting to see that the Intel card is just below, and Celsio is using a different scheme on sending packets. So it's coalescing packets on the transmit. So it's probably doing less DMA transactions, and that's why it has a difference with the Intel interface on the TX. But that's rough numbers, but the Intel and Celsio implementation, they're really close to what DPDK is getting at the moment, which is a full user space driver implementation. So this is how we think it's going to work in the end. You have your user space application, which can be ODP, VPP, DPDK, or whatever you're going to use for TSN or automotive in the end. And we have a library that we can provide. As you can see, the kernel driver is still in there. You can still see the card, you can access the card, you can do an if config on it, you can change the MTU, you can change the number of queues. While you can't do any of these, if you move the driver totally to the user space, you have to re-implement every one of these. So essentially what we do is that we map the RxTX descriptors and the only MMIO region that you need to ring doorbells to start the transmit and TX, and then we move the whole thing to user space. We still leave the descriptor allocation is still happening on the kernel. So the driver is doing the descriptor allocation, we just map the descriptors, and then we allocate buffers for the payload, and we map them back to the interface. So this is an overview of the key differences right now. Now means what the kernel does, and the thin line you can see is who handles the interface. So at the moment, if you use the Linux kernel, the interface resides on the Linux kernel, you have full configuration of it. And this is the Linux kernel is allocating the descriptors as well. And upon receiving and transmitting packets, they end up to SKBs, and they end up your user space as sockets. Now, if you use what DPDK is trying to use, doing VFIO PCI or UIO, which is the older implementation of the same thing, the device moves up to the user space. So you have to reconfigure it. The descriptors move up to the user space as well, so you have to do the whole thing from the user space. And then you have to allocate your user space buffers and handle everything from there. So this is pretty much what we're trying to do. The device will stay on the kernel. So the kernel will still be in charge of interrupts, of everything. The only thing that's going to happen is that the kernel is going to allocate, this is trying to indicate a memory mapping. So the kernel is going to allocate the descriptors, and it's going to memory map it to the user space. And then you're going to allocate buffers from the user space. You're going to map them back to the interface, and you're going to handle the whole traffic from the user space. This actually resides in the middle and says will change, because at the moment we're doing something tricky for the buffers. We're allocating from the kernel, and we're mapping them to the user space as well. But this is already changing, and we're going to do the other way around. We're going to map it, we're going to allocate it from the user space and map it to the device. So this is an overview of how IMMU works. It's called IMMU for Intel. It's the same implementation. It's not the same implementation. It's something similar for ARM, which is called SMMU. And you also have the VFIO framework that we use to achieve all this. So the IMMU group usually means a VFIO group, and the read-only means that this is topology dependent. You can't unmap the devices from the group that they reside in. So when the kernel boots up, it programs the devices, programs the IMMU, and they end up in devices behind the same PCI bridges or behind the same the same functionality end up on the same group. So the IMMU driver is trying to configure that, and it's trying to assign the groups to domains, and domains means a set of physical addresses that the peripherals are allowed to access. So what the VFIO does is that it tries to encompass multiple IMMU domains to the same VFIO container as they call it, and then the devices on the same container can talk to each other safely, and the I/O between them is allowed. So what VFIO does is that usually one IMMU domain means one VFIO domain, but there are cases that you need to attach multiple domains on the same container to make everything to work. So you end up with groups added to containers, and they end up on the same domain, so that they end up sharing the same physical address. That's how you can do zero copy. So as you can see, yeah, this is the MMU, this is your virtual address, your host physical address, and what the MMU does is something similar to the MMU, so you have an IOVA, and it ends up being translated to a host physical address. There are some limitations on this. For example, devices behind the same PCI bridge will end up on the same group, and there's nothing you can do about it. And the IMMU can interoperate between devices if there's no peer-to-peer access, because there are devices that allow peer-to-peer communication through DMA. So you don't go through the IMMU, and there's nothing you can do at that point. So this is what happens on the kernel when we try to allocate to make the whole thing work. First of all, we still leave the kernel doing the work of allocating the descriptors. And we have a module that does exactly what it says. It adds the mediated device regions. So you get a bunch of regions adding of where the descriptors are, what's the length of the descriptors, how many numbers, what's the length of the queue, what you need to map on the user space in order to make the device operational. And then you wait for a transition event. Transition event is actually when the user space application that's going to use the buffer is going to launch. So at this point, the kernel is still in charge of everything. You still have traffic on the kernel. Nothing is broken. You can still have I/O from the kernel. And the kernel just waits for a user space application to pick up the buffers and start the traffic on the user space. So once the transition is received, we're setting the NIC to something we call a transition state. And the transition state is hardware dependent. It depends what you need to do on the hardware in order to have it operating on the user space. It might be just a consumer and producer reset, so you can sync up the user space and the hardware, and it can end up to a full hardware reset depending on what the hardware needs. So after that, once we figure out we're running on a mediated device setup, we're just blocking the kernel TX path, and we're masking the RX interrupt, so there's no NAPI calls or anything like that stealing our packets. We inform the NIC that there's fresh user space buffers it can use to copy the incoming data, and then the packet flow starts on the user space. The kernel has no idea what has happened. He's not transmitting any traffic, he's not receiving any traffic, but the interface is still there for the kernel. So you still have a network interface. Now, this is what we do on the operational side. So we have a module parameter that you need to load at the moment that you're going to instruct the kernel that this is a mediated devices module, although it doesn't affect the operation overall until you actually trigger it from the user space. So there's a function called mediated devices add essential. You have to add it on, this is the changes that you need to make on every driver on the Linux kernel, and that's less than 400 or 500 lines of code on each interface. So what you do is that you get an inventory of the memory regions that you need to map on the user space. So this is usually RX, TX descriptors and doorbells, MMIO for the doorbells that you need for the network interface card. So each region is exported using a struct that's currently on the VFIO API, and it's actually there to support extra regions. So it's probably used the correct way because it's there to support user-defined regions for the VFIO. So the regions we currently support are MMIO, receive ring, transmit ring, and buffer pool. And the buffer pool is actually dependent on if the hardware uses the tape mode or slot mode we discussed in the beginning. So if the hardware uses a slot mode, you don't need the buffer pool, you just need the descriptors. So after that, the VFIO mediated device module from NVIDIA actually creates the files you need in sysfs. And as we said, the I/O is still handled by the kernel at this point, so you have a device that's ready to be handled from the user space once you trigger the whole procedure. But at the moment, it's still operating on the kernel. So what we do in transition, okay, we try to gracefully tear down the RX and TX, which might not be so graceful because we end up stopping the interrupts or masking the RX interrupts. And we're at least we're trying to keep the carrier up if possible, because it's important for some operations and some programs some carriers to keep the interface up if possible. So after that, our module inserts the mediated device flag, so the whole driver knows that the module is actually handled by the user space as well. And we set the hardware to the transition state. As we said, this is hardware dependent. We had hardware that we could just reset the producer and consumer index, and we could make it work just by that. And we had hardware that we had to fully reset it because there was no function to reset the indexes. So another thing that we can do, but we haven't done until now, is that we cannot intercept RX interrupts and redirect them to the user space if needed. At the moment, we didn't need to do anything like that. We always had the kernel handling the interrupts for us, and we masked the interrupts that weren't supposed to arrive anymore. But if there's any need for any device interrupts to end up in the user space, you can just use the device flag that we've set, and you can redirect them on the user space by intercepting the kernel interrupt handler. So after that, the only thing you need to do is that you need to allocate RX and TX buffers, and you have to map them to the user space. At the moment, as we said, we're doing something weird. We have an IOCTL, so we send the IOCTL from the user space. The kernel allocates that memory contiguously, and it maps it back on the user space. And then from the user space, we inform the device for that memory. But this is bound to change, and this is bound to change really quick. We're going to do everything for the user space, from the user space, and we're going to use the VFIO API to map everything back to the hardware. So at this moment, kernel can't do any more I/O. You cannot have traffic on the kernel. The traffic is passed on your user space driver, but the device is still there. So this is what happens from a user space point of view. So the first thing that you need to do is that you need to create a mediated device using the sysfs files that were created during the operation. So you echo a UUID on the mediated device, and you get a dummy device that's on its own group, on its own IMMU group. And after that, you need to figure out that the group is viable. You need to add it on a VFIO container, which is going to be on the same container with a parent device. And after that, you just need to figure out what you mapped from the kernel. So there's a procedure to discover whatever you need. You get back IOCTLs and messages for the memory that you mapped from the kernel, how long it is, what you need to do to map descriptors back to the user space. And this is all done via the VFIO API IOCTLs that are already there. So you iterate through each number of regions that you receive after the discover, and you figure out what you need to map in order to make your interface operational. Then you need to inform the network interface cards for fresh buffers, and this is again hardware dependent. Usually it's just ringing of the doorbell of the interface to figure out where the buffers are, and your transition is complete, and the whole traffic just moves to the user space after that. So this is the operation walkthrough of the user space. You start off by giving a UUID on this path, which is automatically created when you create the mediated device from the kernel. And then you need to do some IOCTLs on the VFIO. You need to get status to make sure that the group is viable and accessible. You need to set the container, so you need to add the group on the container that the parent resides in. And this is going to end up on the proper IMMU domain, so you can have shared access between the mediated device and the actual VF, or between the hardware NIC or the VF or whatever you expose from the network interface card. You need to set the IMMU to enable the IMMU model you want, depending on type 1 or SPARP or whatever hardware you're running to. And after that, you discover the device types. you don't really care. You can get the information that the device is PCI, but you don't really care from the user space. As we said, we're trying to keep it bus agnostic, but you can figure out on what you're running to if you need. And then you discover the device and map the regions back. So the last IOCL you have to make is the VFIO get region info, so you get the type, the size, how long the descriptors are, and you map the device and you map everything to the user space. After that, you need to allocate the memory, because you actually need memory for the payload buffers. This is depending on the NIC again. If it's slot mode, you need to allocate packet arrays and feed them to the network interface card. If it's a tape mode, you just need to allocate an unstructured memory of area, and you just need to inform the network interface card that this is where the memory resides. This cycle will remain, and this is how the VFIO API maps the data to the IMMU and finally to your peripheral behind the IMMU. But at the moment, instead of issuing this on the container that it's supposed to go, we do it on the device, and we map the memory from the kernel, as we said, allocate the memory from the kernel and map it back to the user space. So the last thing you need to do after that is you need to update the hardware. So you need to inform the hardware where the new memory is for it to place the incoming packets. For TX, it's different because you just need to update and say, here's the packet you need to transmit. For the RX, you need to let it know where it can start copying packets. So after that, you signal a transition, which is an IOCL, which is not necessary at the moment, but we have it as an option. And the kernel does whatever it has to do to continue the operation, so your whole traffic is on the user space at the moment. So here's some things that we need to do, because the whole project is an idea. We've proved that it works, but there's tons of work to be done yet. The first thing that it needs to change, and it needs to change really fast, is that we need to allocate the memory properly from the user space and map it to the device. There are some changes that will be required to make to the VFIO API in order to do that. And there's another thing that has to be done on the IMMU drivers of the Intel and ARM CPUs in order to support the whole thing. The idea is that when a device is behind an IMMU and it does a request, you get a requester ID. So at the moment, even if we split the device to kernel having the device and the mediated device buffers, you still get one requester ID. So there are both of those groups, if you say it's separate groups, that's what Linux kernel does at the moment, they have to end up on the same container in order to have everything operating properly. Now, the proper design on this and the proper solution on this was that every time you create a mediated device, the Linux kernel has to figure out that the device is already a part of the group, and the mediated device needs to end up on the same group no matter what, because there is no hardware supporting extra groups behind that. So we need to try and expand the whole network, the whole API to more than network interface cards. The crypto devices from Huawei have similar functionality. I mean, it's data and doorbells that you ring to get and transmit the data. There's an interesting feature from mostly on Intel CPUs, which is called direct cache access. So instead of having the cache back to your host memory, you can have it directly on the cache, and this will speed up the whole procedure. And it might be paramount and very important for 100 gigabit cards or 200 gigabit cards to save the whole cache misses and prefetching that you have to do. There's a very interesting proposal from ARM at the moment on the Linux kernel mailing list. For this SMMU, there's a feature on SMMUs called Process Address Space ID, and it's essentially doing the same thing, but it tries to isolate devices based on a process space ID that it gets. So every device essentially just accesses one virtual area of your user space based on the process ID that it's acquiring the device. And actually, I'm not aware of any other network interfaces cards, but I'm pretty sure Mellanox has one, although I haven't seen any driver taking advantage of it yet. So instead of having SRIOV that you did and you have different virtual functions per interface, you can have one interface and you can have different process space IDs depending on what you require from the user space. The last thing is, collaborate with Huawei, because as we said, they have a really similar approach to crypto, and there's the presentation, I think it's tomorrow, and it's pretty close to what we're trying to do for Ethernet, and it's doing the same thing for crypto. If anyone is interested, there's a proof of concept driver, and it's there for a really cheap network interface card. I think the E1000 is less than $25 euros or something like that. So you can download the source. This is the Linux modifications needed for the mediated device drivers, and below there's the mediated device framework in ODP as it works right now, with the packet generators that we use, with the whole framework that we use to achieve those numbers. And you can just take it, compile it, and figure out how the whole thing works. We'd really like some input. So that's it. Thank you.
So you've put this together for using ODP to prototype.
Yes.
Have you looked at getting DPDK to use the PMDev interface?
Not yet. We haven't been able to do that. But if you keep in mind that the whole API we provide is just an access on sysfs because we don't need anything else. It should be really easy to port across DPDK or ODP or whatever it's supposed to work. It has nothing to do with the kernel.
Right.
It has, you get the kernel part, which is irrelevant to DPDK, to be correct, and then you get a bunch of libraries that access sysfs and create devices. And there's actually no bond to ODP specific.
Okay. Another question. This is a little bit higher level, or a little bit broader. Having worked through this and what you need to do to get this all out to user space, do you have any thoughts on what you would do with the hardware design? Is SRIOV providing what you need, or would you change the interfaces that hardware is providing?
Okay, SRIOV is one proper approach because you can have multiple interfaces. I'm actually thinking if the process address space ID is a better approach than the SRIOV at the moment, then I haven't been able to pin everything down in my head and figure out exactly what to do. That's why I would really like access to a Mellanox NIC with process space ID support, trying to figure this out. But there's a problem on that. There's a problem on the whole design because, for example, you have cards like Celsio that have two ports, and if you don't use SRIOV or if it's not supported for any reason, then in order to do the mediated device stuff, you need to do both ports. There's no way for you to separate the physical function on the PCI bus. So if you don't, SRIOV is the first option, process space ID is the second option, but I really don't know which one is better at the moment. I know Huawei is doing process space ID for the crypto.
I have two questions. One question, what about running this in virtual machines? It seems like you either lose a lot of performance or you need extra hardware to do the two-level IOMMU, right?
Correct, but at the moment, is there IOMMU support for virtual machines?
I don't think we have virtualized the ARM SMMU. Other architectures certainly have it.
All right. No, we haven't been able to run it, but the original mediated device idea from Intel and NVIDIA was for that. It was exactly for what you're saying. So we haven't been able to touch that simply because there's no MMU support, and that was the original goal. The original goal for us was that you have hardware that provides security. Okay, I don't know how that sounds now. But you have hardware that provides security, so we only wanted to move the buffers to the user space, and we didn't have in mind virtualized environments at the moment.
Right. So basically, anytime you add an IOMMU, you lose a lot of performance. You already lose the first performance by allocating from user space instead of allocating from kernel. You lose a lot more when you virtualize the IOMMU.
No, we haven't seen any penalty loss on the IMMU, to be honest. Not at all. We've run this with and without IMMU, and the numbers were exactly the same.
Maybe you're just not running into that limit.
Well, okay, to be honest, we've run the test that does no packet processing and just does raw packets per second, and we've seen no packet.
If you don't access the packets, then
yeah, right. Yeah, you're fair enough.
The other question is about flow control. So for TX, how do you control
disabled? We disabled for the tests.
But yes, but any real application would have to use flow control to control the length of the queue, right? So
yes.
How do you do that if you don't have interrupts?
You can move the interrupts on the user space. You can move the flow control interrupt on the user space, and you can handle that through EventFD if you want.
But isn't that slow?
I haven't tested that on 40 gigabits.
Always sound horribly slow to me. So And
Well-
that's been one of the main problems with all the other user space I/O frameworks,
Well,
that getting the flow control right.
Okay, the flow control might be an issue, but the problem, the thing is that you don't have any other slowdowns on the memory. Memory is memory, whether you handle it from the kernel or from the user space. You're just gonna have the same access. So I don't know about the interrupts though, because we haven't, the problem is that we've only done proof of concepts on this, and we've only run generators with millions packets of seconds per second, but we haven't done a real implementation. So we don't know what will happen if we move the interrupts on the user space.
Well, once you have a line rate application, you're not going to want to take interrupts anyway, even for flow control.
The problem is once the application is faster than the NIC,
Yeah.
you have to stop the application
have to
from
stop the
sending,
application from
otherwise you
sending.
fill up the queue and get buffer bloat.
Well,
No, but would you not want to build that right into the application?
Right, but it has the application has to have a way to find out how much data it has sent in order to know whether it should send more.
Yes. So, I mean, this comes down to the same thing, is would you get the application to pull for that information instead of taking an interrupt to get it?
yeah, you could.
Not the
Yeah.
right way, yeah.
If you look at even
No, you don't want the TX ring to ever become full. You want to stop before you ever get there. You want to make the TX ring as short as you can without ever missing the chance to send a packet. Right?
Actually, if you keep increasing the TXQ, there's no performance gain after some point. It's just a matter of how
No, it
fast the interrupt,
it
the
gets
network
horribly
card.
slow if you go beyond a few microseconds of.
You mean concatenating? Yeah,
If you go beyond a few milliseconds worth of data in the queue, you just add latency. You don't want the latency. This is all about reducing the TX latency.
well,
But if I may, you're talking about latencies that are milliseconds or microseconds. At 100 gig, we're at the nanosecond level. And if you want to actually generate an interrupt, the fastest time that ENIAC can do is half a microsecond. And you still have all those packets that have traversed, and maybe you want to have that. So the interrupt, by essence, cannot address the topic. So it is the responsibility of the application to make sure that it has the right, or it has the proper context to send the packets. The interrupts, when you go beyond 25 gig and 50 gig, interrupts are too slow to inform the application that something goes wrong and it has to react. The application has to handle it directly.
You don't use the interrupt to inform it that it goes wrong. You use the interrupt to inform it that you can start sending again.
So starting, then you have the delay, the latency delay to send the packet, and again you're out of the envelope you would like to stay in, because by the time you get the interrupt, you still have you're still in the microsecond delay, and maybe to meet your other contracts, you still have to be much faster, and polling a memory mapped I/O area would give you a nanosecond, or let's say 10 or 20 nanosecond delay to know if it's time to do that. And you can just piggyback this trigger as you poll for the regular packets. So that's a change of mind in application design. And just mix in the fact that the interrupt latency is way beyond the inter-packet gap. If you're a 1 gig interface, absolutely true. Interrupts are the only way the most efficient, the most economical way to handle the situation. When you go 100, 200, what I said, starting at 25 and 50 gig, you have to remodel your application to match the contracts.
So you say the only way to do it is to just keep wasting CPU cycles in the user application.
Yes, and even worse, you can't even have logs, because logs, you don't even know it, but that's massive part of the cost of introducing massive latency.
actually we had worse. We usually try to assign one CPU per core in order to avoid locking, at least in the ODP. And whenever we had locking, we had performance loss.
So I probably have a few questions here. So first question is, so my understanding is this solution, you redirect all traffic to user space. And the target goal is to get like maximum throughput on a big
Or
network.
minimal latency as well.
But how it can be reused on use cases where we do not need such a big throughput, but instead we need to support things like this. We need to handle generic traffic in a regular way.
Okay, so you need RSS to split the queues and have half of them on the
Yeah,
kernel and
so
half of them on the user space.
Just pair of queues need to be exposed to user space, and usually it's kind of there
Right.
is a big demand for this
Right.
requirement.
This actually depends on the NIC implementation because every queue, at least on the high-speed network interfaces that we saw, every queue has its own doorbell and its own descriptors. So if you make sure that you populate and consume those from the user space only or from the kernel space only and keep them in sync with each other, and not with each other, with the kernel space or user space they reside in, you actually have no problem. So for RX, let's take RX for example. You need to inform the NIC that you have buffers for it to fill in the packets. But every queue has its own doorbell, right? So if you make sure that you write the correct memory values on every doorbell, you don't really care. If the RSS takes care of where the packets end up, the NIC is going to continue working and you're going to have half of the traffic on the kernel and half of the traffic on the user space.
So you mean it's required to create a separate dev for just to handle this
Yeah.
to queue?
You need to have RSS pre-configured. That's why mediated devices is good because RSS is usually configured from Ethel, right? So you use Ethel, you split the queues, and you let the kernel handle half of them or whatever you want, and you let the user space handle the other part. This is not as easy as it sounds, but if the network interface cards have doorbells per queues, then this is doable.
Yeah, no, there are actually few use cases. You can transmit the same way as it's the regular way, but receive in an exposed queue.
Okay.
There can be a pair of queues. They're usually in embedded. There are not a big rates. It's like usually 100 megabit per stream, something like this. And yeah, so the application need to run on separate CPU.
Yeah, but
not a kind
from a
of-
hardware point of view, this is doable.
but we need to have like full control on hardware using the standard interface.
Yeah, that's the good part, that you keep the interface on the kernel, so you don't have to change anything on your scripts. Okay, I understand that ifconfig might not work to configure the IP address, but you will still have Ethel to configure the number of queues. You'll still have Ethel to dump the descriptors, you'll still have Ethel to query the interface for stuff you want or configure the physical behind it.
Okay, so this is the next question. So how can it work in case if there is no AMU?
Yeah.
Still can.
Yeah, yeah. It's IMMU is not a must. We just use it because it's convenient and it's really good for us to separate the traffic. Because if you do something wrong on the user space driver, you'll not end up crashing the whole thing. You'll end up crashing a memory area that's yours.
So I would imagine this should be safer without an MMU than regular SRIOV.
Yes.
Regular VFIO.
VFIO.
Because VFIO, you're providing the whole context of a virtual device to user space, and user space can program that device to
But-
send packets to anywhere in memory if
The
there's
only-
no MMU.
The only
If it's-
that's-
Yeah, if it's with this, where it's just the queues that are being exposed, then the kernel driver is still in charge, and it can constrain what the hardware is programmed to do.
There's just one catch over there. You map an MMIO region, and you need to map on a page granularity. So you might have access to different firmware, soft firmware, NIC firmware things that you're not supposed to. But if you do page faulting or stuff like that to try to limit the page mapping, you're gonna get too slow on accessing the
So it
MMIO.
depends on the hardware vendor for the
Exactly. It depends on what's next to you because we had NICs that had the doorbell on bar 0 and we had NICs that had the doorbell on bar 2.
Right.
So that's totally dependent on the hardware, and that's the question that comes in, that do we need to speak with hardware vendors for that?
Yeah.
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 I'd actually like to see some guidance and stamps on that. There's on how
Yeah.
to build future hardware.
The other thing with the IMMU is if your buffer is small enough that it completely fits into the IOTLB and nothing else uses an IMMU, then you're always fine. The problem is if your buffer either gets bigger than the IOTLB or you have multiple devices using the IMMU at the same time.
Correct.
Then you get the performance problems.
Correct. I've seen reports saying, okay, there's 20% loss or 15% loss, and I was saying, okay, that I don't see any loss. I don't know what they're talking about.
I think you can easily get to 80% loss if you get into the worst case.
Probably.
And from the last question from my side, so it looks like it's the similar work, very similar is done with HTTP socket. So and you're doing similar things kind of in parallel. So
It's AFXDP is trying to do something more secure from a software point of view. They're not allocating. We're allocating the descriptors on the user space, and we are allocating the buffers as well, and then we map them to we inform the hardware about the new buffers. AFXDP is trying to do something different, so it maps the buffers from the kernel, it memory maps them to the user space, but then it provides an API between the actual hardware descriptors and the software descriptors that you fill in on the user space. So it's a kind of a different approach, because we expose real hardware on the user space, they expose dummy descriptors on the user space, and the memory buffers only. But at the moment, while the idea is pretty good actually, I don't know if they'll be able to support network interfaces cards that don't work on slot mode. And you need to pass a memory area that.
So for AXDP, I had a great discussion with them at FOSDEM last month, and they don't move the packets, but they create and copy descriptors from kernel to userland. It looks good. The solution works very nicely. However, in terms of performance, that's changing. And if again we go to 100 gig, I'm always talking about 100 gig because LNG members are large network equipment vendors that need 100, 200 and more interfaces. So if you look at 100 gig at line rate, that occupies just the packets, that occupies one DRAM channel entirely. If you have a two cache line descriptor for that particular thing, you're then consuming 2 additional DRAM channels. So for incoming packets, if you have AXDP sockets, you're consuming 3 incoming DRAM channels for
the data.
For the data and the descriptors. So here we are trying to avoid those 2 DRAM channels because we need applications that will ask the memory for, if it's a DNS server, you want to have still access to the memory. If it's a provider edge router, you have 4 GB of routing table, so you need to have access to the DRAM. So even though the architecture is very clean and secure from a design perspective, if you want to go to the fastest possible network connections, then you have a problem.
yeah, but then I'm trying to understand what I can expect to have like in a year in mainline, and what we can commit to or expect from our side to use, because we are not working with very high-speed connection. So do you expect to have like 2 solutions in upstream kernel to do kind of similar things, or what containers thinking about this?
He's probably better suited to answer on the
Yes.
lab streaming.
So one aspect that I always see in the network stack in Linux is that all the acceleration features are exposed to user space in a way that they're completely hidden. And with AFXDP, the one feature you get that this does not is that it works whether or not the hardware actually makes use of it. So AFXDP looks exactly the same to user space on a dumb NIC that doesn't have any of those queuing mechanisms as it would be on a 100 gigabit NIC. And obviously here you already have the difference between different vendor drivers.
That's what you have to do on the user space anyway.
Yeah.
Right, and the other thing is, it is actually really hard to have 2 interfaces doing the same thing, getting merged into the kernel.
And it's really one to hard exposing hardware features to.
It's, and fun as well, if you're not sure whether or not you need user space offload and data plane? You probably don't. I mean, if you're, the user space I/O, this is, and we're talking data plane, we're talking about packet inspection, we're talking about things that the Linux kernel stack is not fast enough, and you want to really cut down the number of things that are being done to your very specific application. You really need to know what you're trying to do. If you don't know that you need data plane, you probably don't need it. You probably want to use the Linux kernel stack and just those
The
interfaces.
question is, it's still useful and still we need some time to write drivers in user space. Not because we need like high throughput, because we need a small latency.
Okay, but the thing is that if you have to move your whole driver to the user space, you're looking at replicating the user driver. If you're looking on exploiting descriptors only, you're looking at 500 lines of code with interfaces and 100 gigabit one.
Yeah, but anyway, so when we do something like this, we got code which we need to support internally. And so basically we're interested in having a solution which we can use. And this is discussed for a few years already, like how to expose these rings. And a lot of things block it actually because of security.
My point of view is that if you have IMMU and you're guaranteed not to crash the whole thing, personally I think it's fine. You're in charge of what you're doing on the user space. You should know what you're doing on your hardware. So I don't see any other. There are definitely more security implementations.
We can take a very concrete example. And I will take the Intel one. The Intel 40 gig card is probably 30,000 or 40,000 lines of code.
It's 55, 52, something like that.
55,000 lines of code. The DPDK driver is roughly the same, less, probably 40,000, because they don't cover all the hardware flavors or the hardware revisions and the combinations of firmware, etc. So it's not exactly the same thing. And our driver is less than 1,000. So it's your choice if you want to maintain 40,000 or 1,000. And it won't change based on the firmware or the hardware revision, because all those things are handled by initialization code, which is done by the kernel. So if you have a team of guys that do handle your hardware in the kernel, the expertise is there, should stay there, they're in control of the charge. And then you expose
what they want.
only what's needed.
There's actually no point doing the resets outside the kernel.
The question is that sometimes, so that because there is no standard interface, we need to use UIO, or we need to put kernel with driver, then do some initializations and do some IO control, which will configure everything, like expose memory, mapping, and so on. And then small driver, which actually just doing DA network and DMA, this kind of thing. But this is not upstream.
Not yet. Now, I talked to...
We're gonna try.
To have something like...
This would be upstream.
Huh?
Yeah.
We're really gonna
So
try.
for this activity, you have to know that Intel is working on a very similar, Intel and Red Hat are working on a very similar scheme, but the only consumer for that is QEMU. Well, we want to have that not just for QEMU, but for any user I/O program. And this is also in line with NVIDIA interests, where they wanted to expose GPU.
They have that, and it's probably
They
proprietary.
have that now.
Yeah, it's vGPU, and I have no idea exactly what they're doing.
But then they may need additional features, and then that's a way to extend that. So, talking to Red Hat at first, there were no major hurdle in upstreaming. It's just for us to start and get feedback from the community. The AFXDP guys also are not guaranteed upstream, because Dave Miller asked at least 2 vendors to support the AFXDP, and for the moment there is only one vendor. So I would say there is a race to make sure that we start the proper discussion in the kernel to expose what we bring on the table, what's different, better or less good than AFXDP. And the future is not written. We have to.
Another thing that you can expose on that, and you can exploit on that AFXDP can't at the moment. Imagine that you have a PCI transaction limit, right? And you have an MTU on that, which is 256 bytes. So if you keep doing 64-byte packets transactions, you're gonna pay the overhead for pretty much every packet you transact.
I don't have PCI.
Okay. Don't you have overhead on the whatever bus you're doing the transaction. Okay, so USB has been doing this for, I don't know, 10 years on the 1 gigabit interface. You actually concatenate the packets. So you place 64 packets, the one behind the other, and you pay the transaction price once, and then the network interface card is responsible of segregating the packet and sending it up again. So you can send 3 packets with one PCI transaction, 3 64-byte packets. So you can essentially pick what the PCI transaction limit is for packets per second, which the AFXDP can't at the moment. And I think that's things that have to be considered as well. I'm pretty sure that was irrelevant to the interface that we want to use.
One question on the traffic segregation between kernel and the user space.
No, the NIC is just the firmware on the network interface card is able to pick up the 3 aggregated packets and split them before it actually transmits it.
Okay, and my question is on a different topic. Sorry if you want to continue this discussion.
No,
I
that's
can ask after that. Okay, so we talked about.
I think I'm out of time.
Okay.
Long ago.